Hey everyone, welcome back to the channel. In today's video, we'll discuss the fascinating world of Linux IP routing. This episode will be a bit theoretical, but I'll try not to be completely boring. We'll discuss some basic concepts like routes, route scopes, route tables, routing marks, and policy-based routing. By no means it's not a comprehensive routing tutorial, but just enough to get you started. We'll look at the routing from a single Linux host perspective. My name is Philip. Let's dive right in. If we look at computer networks from a high-level perspective, we'll see a bunch of routers, switches, firewalls, and other networking devices interconnected with each other. When data travels from source to destination, routers and other networking devices examine packet headers to determine the best path for it to travel, and then the packets are forwarded accordingly. I'd like to start by pointing out a subtle difference between routing and forwarding. Those are two related but distinct processes. Routing is the process of determining the best path for data to travel across a network from source to destination. Forwarding, on the other hand, is actual process of moving packets from one network device to another or from one network interface to another network interface. To make a server act as a router, we need to enable packet forwarding. By default, packet forwarding is disabled to prevent server from unintentionally routing traffic. So, the first thing we need to do is enable packet forwarding on our server. To do that, I will open kernel configuration file and uncomment lines responsible for IPv4 and IPv6 packet forwarding. Let's save and apply the configuration. Now, our server can forward packets between the networks. What's next? When a packet is received, our server needs to determine whether to deliver it locally or forward it further to the next hop. If a destination network is not directly connected, we need to rely on other routers to reach it. There are three basic IP destination classes. Local, those refers to IP addresses that are assigned to the local machine itself. Apart from the interface IP, there's also an 127.0.0.1 address assigned to the loopback interface. That's basically a virtual network interface used for testing network applications or communicating between applications within the single computer. The hostname associated with this IP is localhost, and it refers to computer you are currently using. In fact, all addresses in 127/8 network point to the local host. I can ping any other address from that range to get to the local machine. Next IP destination class is called connected networks. It refers to destinations that are directly reachable via a network interface on the local machine without needing to pass through a gateway or router. For example, ETH0 network interface is configured with 192.168.80.51/23 address, so any IP within that /23 range is reachable. So we consider this /23 a connected network. Obviously, the traffic to connected destinations is sent directly out to the corresponding network interface. Finally, we have remote networks. Addresses in that class are on different network segments, so routing is required to reach them. In other words, if we want to send data to a remote network, we need to send it to another router that in turn will forward the packets toward the final destination. Mind that the router must have an IP address in local reachable IP address range so we can get to it. It needs to be directly connected. Just to sum up, as far as the reachability goes, there are three major classes. The IP address can belong to the local machine, or IP address is reachable via a directly connected link, or IP address is remote, so we need to go via a router that's on a directly connected link to get to it. In order to send packets to a specific network or IP address, Linux kernel needs to check for a route. A route is a rule that defines the path that packets should take to reach their destination. A route has multiple properties, but the most important ones are destination network, that's the IP address or network to which the route applies to. Next hop, that's the IP address of the next router through which the traffic should be forwarded. And the interface, that's the network interface used to reach the next hop. So to get to Google DNS, a remote IP that is not directly reachable, we need to send the traffic to 192.168.80.1 IP. That's our next hop via ETH0 interface. Mind that the next hop needs to be directly reachable, like in this case. The next hop is on the same /23 network segment. If we check a route to an IP address on a local networking segment that's directly reachable through the specific interface, we won't see a gateway specified, just the destination and the interface. There are more route properties, but for the time being, let's consider only destination, gateway, and the interface. Before we proceed to routing tables and routing policies, let's briefly discuss route scope. A route scope defines the visibility of a route. There are primarily three types of scopes. Host scope, such routes target specific IP addresses directly on the local machine. Let me query all routing tables for host scope routes. I will just issue an IP route show and add the scope host parameter. Please notice that host scope routes show only IP addresses or network ranges assigned to the local machine itself. We can see the interface IPs as well as 127/8 loopback network range. Second type of scope is link scope. Such routes are used for target addresses within the directly connected networks. These routes apply to destinations that are reachable without going through a gateway or router. Let me query all routing tables for link scope routes. Notice there are /24 routes directly reachable via respective interfaces, as those are on the same networking segment on the same link. Apart from regular unicast routes, you will find broadcast routes there. Broadcast addresses target all devices on a specific network segment. Mind that the operating system assigns those interface and broadcast routes for us automatically. Last type of scope is global scope. Those routes cover destinations that are beyond the local network and require routing through one or more intermediate routers. A perfect example of such global route is a default gateway. It is the next hop for the traffic that does not match any other specific route in the device routing table, essentially a catch-all route. Do you see how scopes correlate to destination addresses? Host scope aggregates local destinations, link scope aggregates connected networks, and global scope aggregates remote networks. Let's switch gears and talk a little bit about routing tables. Routes are grouped into tables, and the Linux system then uses those routing tables to determine the best path for outgoing packets. You can have multiple routing tables. The RT tables configuration file in etc IP route 2 folder maps numerical identifier of routing tables to a human readable name. As you may guess, there are three tables available out of the box. First, there's the local routing table. It's a special table maintained by the kernel that contains routes for addresses assigned to the local host. This table cannot be directly modified. To see the contents of that table, let's issue IP route show and add table local to indicate the table we want to display. Local routing table essentially maps IP addresses to the network interfaces. Next, we have the main routing table. This table is where the majority of the routes are stored. It contains directly connected networks, routes to specific IP addresses or subnets, and the default route. The main routing table is populated automatically by the kernel when new interfaces are brought up with an IP address. You can omit the table main parameter if you'd like, as the IP route command manipulates the main routing table by default. Important thing to mention is that we can have up to 255 routing tables. 3 of them are used already, so we are left with 252 tables for specific purposes. To dive deeper into routes, let's analyze our very simple networking diagram. We have a server that has 3 WAN networks attached. ETH0 with 80/23 range, ETH1 with 10/24 range, and ETH2 with 12/24 range. Each network has a gateway that can be used to get to the internet via a different internet service provider. Additionally, the server has 2 more interfaces, ETH3 with 10.100/24 private network and ETH4 with 10.200/24 private network attached. Each private network holds a client device with the default gateway set to the server, a typical diagram, few LAN and few WAN networks. We have multiple internet connections, so let's say we'd like to go to Google DNS via ISP1 attached to ETH1 interface and Cloudflare DNS via ISP2 attached to ETH2 interface. That's easy. I will add a route that points to Google DNS via Gateway 1 and add another route that points to Cloudflare DNS via Gateway 2. If we look at the routes with scope set to global, we'll see the default gateway, that's the gateway used as a last resort, and then two static routes, one pointing to Cloudflare DNS via gateway 2 and one pointing to Google DNS via gateway 1. Let's trace the route to Cloudflare DNS. Packets were sent via gateway 2 with 12.254 address. Let's trace the route to Google DNS. As expected, it went via gateway 1, that's 10.200. If you ask why the traffic was routed via 12.254 or 10.200 and not the default gateway, the thing is, if you have more than one route available to a destination, the Linux will select the best route based on few criteria. First and most important one is called longest prefix match. Basically, the most specific route wins. Let me add one more route, but this time to the whole /24 network. If we analyze the routing table, we'll discover that there are three potential routes to Cloudflare DNS. Most specific one is the /32, less specific is the /24, and the least specific one is the default route. If we check the route, of course the most specific will be selected as the best route. Remember, the rule of longest prefix is the most important rule. What if two routes have the same prefix length and it's a tie? Linux will then use a property called metrics to determine which route is the best. Let me delete routes to Cloudflare DNS and add them back, but this time I will set a metric to 100 for the second gateway and set the metric to 200 for the first gateway. If we look at the routing table, there are two routes for Cloudflare DNS. However, the route that will be selected is the one with the lower metric. We won't be getting into much details on metrics, as it deserves a video on its own, but just so you get the idea. Depending on the routing protocol, a metric can be the hop count, that's number of nodes between a source and destination, or bandwidth of a link, or delay, or load, or cost in general. It makes much more sense when you enter the world of dynamic routing protocols. Dynamic routing protocols can calculate route metrics and adjust them over time based on changing networking conditions. There's one more thing I'd like to show you when it comes to route selection. We can set up routes to be equal cost to load balance their traffic between the routes. Let's set the ECMP hash policy to layer 4. Next, let's check the IP for ifconfig.me site. This site returns your public IP. Finally, let's add a route to the IP, but set the next hop to be gateway 1 and also gateway 2. If we check the routing table, we'll find that the route to this IP goes via both gateways. Let's try connecting to that page. Do you see that? Traffic is load balanced across two links. Last thing I'd like to show you before we move to routing policies are some special route types. We can set a route to be unreachable. When a packet matches such a route, the system responds with an ICMP destination unreachable message to the sender and drops the traffic. Let's try that. We can set a route to be prohibited. When a packet matches such route, the system responds with an ICMP administratively prohibited and drop the traffic. Finally, the most commonly used is the black hole route. Such a route silently drops packets. It's usually used in filtering of unwanted traffic or mitigating denial of service attacks. Lastly, black hole routes are commonly used in BGP as BGP advertises routes that it knows about. If we want to advertise a route that is not in the routing table, we just create a black hole route and then BGP can advertise it. Okay, we know the basics of routes, scopes, and routing tables. By adding entries to the routing table, we can direct the traffic via different paths or filter it. The question is, why would we need more than one routing table? If we look at our networking diagram, we can see two clients. What if we would like to direct all traffic from client 1 via gateway 1 and all traffic from client 2 via gateway 2? We can only route based on destination address. There's no option to route based on the source address. Here's where the routing policy comes into play. Let me show you how it works. I did restart the server, so it has only the default route. Here's a simple firewall rule that performs a masquerade on all three WAN interfaces. Basically, for all traffic going out from those interfaces, the source IP is replaced with the interface IP, so the traffic knows how to get back. Let's apply the firewall configuration. Now let's go to client 1 and trace the route to Cloudflare DNS. We go out via the default route. Let's perform the same trace route, but from client 2. As expected, the route is identical. I will open the file with routing table mapping and add two new routing tables. 100 that maps to WAN 1 and 200 that maps to WAN 2. Next, let's populate those routing tables. I will add a new default gateway via 10.200 to table WAN 1. I will add a new default gateway via 12.254 to table WAN 2. Let's display those routing tables. The main routing table shows the default gateway as 80.1. WAN 1 routing table shows the default gateway as 10.200. WAN 2 routing table shows the default gateway as 12.254. We have three routing tables. Each table has a different default gateway set. Now the trick. There's a routing policy database that tells the kernel which routing table to use. Let's display the routing policies with IP rule command. Rules are processed in ascending order, so first the local routing table is checked, then the main routing table is checked, and so on. I will add a new rule, so if the traffic comes from 10.100/24, that's the first private network, kernel will use routing table WAN 1. If the traffic comes from 10.200/24, that's the second private network, the kernel will use routing table WAN 2. If we display the routing policy database, we'll see two new entries. Let's consult the routing table for Google DNS. To get to Google DNS, the default gateway of the main routing table will be used. If, however, the source of the traffic is the first private network, for example 10.200.0.1, then a different default gateway is selected. Default gateway from routing table WAN 2. Let's test that. I will go to client 1, that's in the first private network, and run the traceroute. Traffic goes via 10.200 gateway. Let's run the traceroute from client 2, that's in the second private network. Traffic goes via 12.254 gateway. The idea behind policy-based routing is to allow users to configure routing based on more parameters than just the destination address. Policy-based routing is commonly used to segregate traffic for different clients or services, route VPN traffic, or load balance the traffic between multiple ISPs. First, the kernel needs to select the routing table based on the originating interface, source IP, or other criteria, and then find the right route to process the packet within that table. A very powerful feature is selecting a route based on a firewall mark. Let me show you how that works. I will remove the newly created policy routing rules and add a new rule. We'll say, if a packet has a firewall mark set to 100, we'll use routing table WAN 1. If a packet has firewall mark set to 200, we'll use routing table WAN 2. We can use the vast capabilities of firewall to mark the traffic. We can mark by interface, IPs, connection state, protocol, you name it. I've prepared a simple nftables configuration file. Here we attach to the pre-routing hook on Mangle priority, and here we do simple marking. If traffic comes from the ETH3 interface that's connected to the first private network, we set the firewall mark to 100. If traffic comes from ETH4 interface that's connected to the second private network, we set the firewall mark to 200. Let's apply the configuration. I will run the traceroute from client 1. Traffic goes via 10.200 gateway. Let's run traceroute from client 2. Traffic goes via 12.254 gateway. Basically, a different routing table is used based on a routing mark set by firewall. Nice. The only issue with this approach is the traffic between private networks stop working. If I try connecting from the client in the first private network, that's 10.100/24, to the client in the second private network, that's 10.200/24, it won't work. The issue we are facing is that the traffic coming from the first private network will be sent to the default gateway and not to the second private network. What we want to do is consult the custom routing tables for the default gateway, but consult the main routing table for directly connected networks. To do that, let's add a rule that checks the main routing table for all routes except default gateway. Let me reiterate. This rule is higher on the list than any other custom rules, so it will be checked earlier. This rule is pointing to the main routing table that has the routes to our private network. However, we are giving a condition that the rule should apply only if prefix length is different than 0. So if we are asking for the default gateway, the rule will not apply, but one of our custom routing tables will be used. If we are asking for any other route than the default, then the main routing table will be used. Let's test the connection between our private networks now. Works. And that wraps our introduction into the world of IP routing. Hope you find this video informative and you are walking away with a stronger understanding of concepts like routes, route tables, route scopes, or policy-based routing. Remember, mastering these concepts is crucial for anyone working with Linux. Thanks for watching, and until next time, keep networking and keep learning. See you in the next video.